Hey guys, what's up? Hope it's going well with you in these difficult times. I'm excited today though. Today's going to be the first day ever we have a full lecture on YouTube, and we're going to be looking at chapter 6. I've done a bit of work in getting the setup nice and clear. I have some nice new pens. So without delay, let's get into it then. So in this chapter we're going to be looking at a uniform motion in a circular path, and as the title shows, as the first slide shows, this can apply to problems such as roller coasters, cars on tracks, planets orbiting or moons orbiting a planet. And essentially it's a short chapter. What we're going to be doing is apply Newton's law to solve problems on this concept. And essentially what we're going to be doing is we're going to be combining two concepts or two equations which we've already derived. In the previous chapter we looked at uniform circular motion, and we saw that for motion in a circle we have an expression for the centripetal acceleration, and this is the centripetal acceleration is v squared over r. You'll remember we used all those that triangle approach to derive that equation. And the second equation that's very familiar to us is Newton's second law, and of course that's simply that the sum of the forces is equal to mass times acceleration. So what we're going to be doing is combining those equations to give us a tool to solve these types of problems. The first equation is Newton's second law. The sum of the forces is equal to mass times acceleration. The second equation is the equation that we saw from the previous chapter, that the centripetal acceleration is equal to v squared over r. And remember, we decided to use the subscript c to denote centripetal acceleration. In this context, we're going to be applying Newton's second law to the centripetal equation context. So substituting equation 2 into equation 1, then we can see that the sum of the forces is equal to m v squared over r. So this is the tool that we're going to be using. So it's interesting for us to look at this force and to consider the role that it's playing in our situation. So we know from Newton's first law that an object will continue moving in a straight line unless it's acted upon by external resultant force. So if we look at this case of our object moving in a circle attached to a string, we see that this force over here is required to persuade the object to remain in its circular trajectory. As indicated in this diagram, it's a force acting towards the center of the circle. Remember, that's because the centripetal acceleration also acts towards the center of the circle. And if it wasn't for this force, what we would have is we would have the case, when this string breaks, this object would fly off at a tangent to the circle, no longer continuing in its circular orbits. So then let's take a look at applying this concept now to solving a problem. The problem that we're going to be speaking of refers to a small remote control car with mass 1.5 kgs. It's going with constant speed of 12 meters per second in a vertical circle inside a metal track, as shown below. What is the magnitude of the force exerted by the track on the car at point B? So as shown in the figure, they're speaking of a little car that's going around in a loop-the-loop motion, and we given a moment frozen in time at the top of the car's trajectory, and we asked to calculate the magnitude of the force exerted by the track on the car at point B. So let's just remind ourselves of the equation that we're going to be using to solve the problem. We remember we're going to be combining the two equations that we saw before. The first equation is the sum of the forces is equals to mass times acceleration. So that's Newton's law. We're going to be combining this with the equation, this centripetal acceleration is equal to v squared over r. And when we combine these two equations, the equation that we're going to be using is the sum of the forces is equals to mv squared over r. So you can see from this problem we're going to be solving it in a similar way to the way we treated the problems in previous chapters. We're going to start by considering the sum of the forces, and in order to do that we need to have an axis and draw in all our individual forces. As before, we place the axis where the object is orientated, and we indicate the x and the y axis. And from this point we go ahead and draw the individual forces acting on the object. So the first force of interest to us, is as always we have the force of gravity, and this is going to be mg, and remember this is going to be in the minus j hat. It's acting downwards. The second force that we need to draw in is the normal force, and this is going to be the force exerted by the track on the car. And in this case the track is going to be pushing downwards on the car, and the normal force is going to be pointing in this direction. So it's also going to be pointing in the minus j hat direction. And remember, what's going to be happening is the sum of these forces is going to cause a centripetal force, which is also going to be pointing towards the center, and the magnitude of the centripetal force is going to be v squared over r. So now that we have our figure, we can go ahead and write the relevant equation. If we have the forces, the first force I've noted is minus mg acting towards the center. There's the normal force acting in the negative j hat direction as well, so I indicate that as minus n, and this is going to be minus mv squared over r. I've included the minus sign because the centripetal force also acts towards the center. We asked to calculate the normal force, so we can simply rearrange the equation. This will give us the normal force is equal to, it's going to be mv squared over r minus mg. So this means that we're going to have the normal force is equals to mass times v squared over r minus g. We can substitute the relevant values in. We're given that the mass of the car is 1.5 kgs. We're given that the speed of the car is 12 meters per second squared, so this is going to be 12, and the radius of the track is given as 5. So it's 12 over 5 minus 9.8. And if you calculate that, then you'll find the solution to be 28.5 newtons. So our final solution for the normal force, the force of the track on the car, is 28.5 newtons. So what I'd like to do now is talk about two different variants or different flavors of this problem that you might encounter. So you may be asked a question about either of these two scenarios where, in the first we no longer have the car at point B at the top of the track, but instead of that we have it at the leftmost position on the track. And no matter what problem you ask relating to the scenario, you will solve it in the same way. You will start by defining your axes. We'll have the x-axis and the y-axis. The next step we will do is we'll draw in the individual forces acting. So we'll have the force of gravity acting downwards, and this is going to be F is equal to minus mg, where the minus indicates that it's operating in the negative j hat. The second force that we have acting on the car is just going to be the normal force, which acts perpendicular to the track on the car. Remember, we're interested in the equation, the sum of the forces is equal to mv squared over r. And what we're interested in is the forces acting towards the center of the circle. So in applying this equation, we would have plus the normal force that's acting directly towards the center, and this would be equal to mv squared over r. This is also the centripetal force also acts towards the center. So this would be the relevant equation. The gravity component is tangential. It's not acting towards the center of the circle, so we don't concern ourselves with the gravity force in this case. If we look at the second problem, we would treat it in a similar way. In this case, we have the car at the bottommost point in the track. Again, we will define our axis in this way as shown, and we will go on to draw our individual forces acting on the car. So the first force we will have is the force of gravity, and again this will be equals to minus mg, where the minus indicates it's operating in the negative y direction, and the second force is the normal force acting in the positive y direction. And when we go on to apply our equation, the sum of the forces is equal to mv squared over r. In this case, we will be applying everything in the y direction. So we see what we have is plus normal minus mg is equal to mv squared over r, the centripetal accelerations acting towards the center. You can compare the signs that we have here to the signs that we have in the previous problem. So then this brings us to the end of chapter 6. As I said, it's a fairly short chapter where we just apply one concept to solve a certain type of problems. If you have any questions relating to the lecture and what we've discussed today, I encourage you to post them in the YouTube comments below, and I'll pass by and answer your questions. Perhaps you can also answer each other's questions, or use it as a sort of a chat and interaction platform. Okay, till next time, keep safe and see you soon.